Welcome to calculus. You will master complex problems, but forget how to add. On this episode, Stevenson will demonstrate Let's talk about continuity. So, when we plot function values generated in the laboratory or collected in the field, we often connect the plotted points with an unbroken curve to show that the function values are likely to have been at the times we did not measure. So here's an example in the figure right here, 1.16. Okay, normally we connect them. So in doing so, when we do that, we're assuming that we're working with what's called a continuous function. In other words, a function whose outputs vary continuously with the inputs and do not jump from one value to another without taking on all the values in between. Any function, y equals f of x, whose graph can be sketched in one continuous motion without lifting the pencil, is an example of a continuous function. That's actually kind of a very simple way to illustrate. If you can sketch something, the entire graph, without lifting your pencil, you can say it's continuous, but I digress. Continuous functions are those we use to find a planet's closest point of approach to the sun or the peak concentration of antibodies in blood plasma. They're also the functions we use to describe how a body moves through space or how the speed of a chemical reaction changes with time. In fact, so many physical processes proceed continuously that throughout the 18th and 19th centuries, it rarely occurred to anyone to look for any other kind of behavior. It came as a surprise when the physicists of the 1920s discovered that light comes in particles and that heated atoms emit light at discrete frequencies. And then that shows us this cool figure right here. As a result of these and other discoveries, and because of the heavy use of discontinuous functions in computer science, statistics, and mathematical modeling, the issue of continuity has become one of practical as well as theoretical importance. To understand continuity, we need to consider a function like the one in figure 1.18, whose limits we investigated in example 8 of section 2.1. That's probably a typo. I think they mean 1.1. Alright, so let's look at this graph here. Now, we've looked at this before here, and in doing so, we practice finding the limits. So let's look at our example and see through discovery if we can try to understand what continuity really means. Find the points at which function f in figure 1.18 is continuous and the points at which f is discontinuous. Let's start with the continuous parts first. So this says the function f is continuous at every point in its domain, the closed interval from 0 to 4, except at x equals 1 and x equals 2. So let's look at those really quickly. 1 kind of makes sense because you see how there's a break in the graph, and 2 makes sense because there's a hole. So it says at these points there are breaks in the graph, and note the relationship between the limit of f and the value of f at each point in the function's domain. Okay, so they're asking us to compare two things. So let's try that. Let's look at x equals 0. So let's look at the limit of f of x as x approaches 0 from the right. Now notice it's a one-sided limit and not a two-sided limit, and the reason for that is because the function only exists on the right side of 0. So when we look at this, if we look at the limit as x approaches 0 from the right, we can see the limit the function is approaching is 1. And what is the function if we evaluate it at 0? It's also 1. So notice this one-sided limit equals the same thing as the function evaluated there. And they told us it was continuous. Let's look at 4. 4 says, at 4, over here, it says the limit of f of x as x approaches 4 from the left, so that's this side right here, is equal to f evaluated at 4. So the limit of f of x as x approaches 4 from the left is 1, and f of x evaluated for is also 1. So again, notice they agree. Now this last one tells us to look at an interval. So it says that any value, they're calling it c, that's between the open interval from 0 to 4. So notice it's not including the endpoints because really they're right there. As long as it's not 1 or 2, which remember we said are problems right there, then this is true. So this says you can take the limit of f of x as x approaches any c number between 0 and 4, as long as it's not 1 or 2, and it's going to equal the function evaluated there. So let's try 3. 3 is between 0 and 4. It's definitely not 1 and 2. So let's test it. What's the limit as x approaches 3? Well, if you approach 3 from either side, we're going to see the function is headed towards 2, right here. And what is the function evaluated at 3? It is also 2. So notice they agree. So let's go to the definition of continuity. So to define continuity at a point in a function's domain, we need to define continuity at an interior point, which involves the two-sided limit. So here's this really nice picture here. I suggest that'd be good to get it down. So when you look at an interior point, you look at the two-sided limit. And when you look at continuity at an endpoint, you look at the one-sided limit. So that makes sense on the previous example why we only looked at one side. So if you're trying to determine continuity on the endpoints, you look at the one-sided limits. If you're trying to look at an interior point, you have to look at the two-sided limit. So what does it mean for something to be continuous? For an interior point, a function y equals f of x is continuous at an interior point c of its domain if the limit of f of x as x approaches c equals the function evaluated at c. In other words, if the limit exists and it equals the function evaluated there, then it is continuous. Okay? So if you look at now the endpoints, the function, the definition here says a function y equals f of x is continuous at the left endpoint or it's continuous at the right endpoint of its domain if the following is true. So essentially, we already kind of saw that in the previous example, right? So if you're approaching a particular left-hand endpoint, this would be the left-hand endpoint because you're approaching from the right, then the function has to evaluate it there equals the same as the limit. And if you have a right endpoint, you'd be approaching from the left. So let's look at what it means to be discontinuous. Okay, so at x equals 1, why is it discontinuous there? So at x equals 1, what's the problem here? Well, think about what we just read about with continuity. The limit has to exist, correct? But it also has to equal the function evaluated. The problem at 1 is that the limit itself doesn't even exist. 1 is an interior value. So both the right and the left-hand limits must agree, but they don't. So that immediately fails, and that's why it is discontinuous, because the limit doesn't even exist. Now, why does x equal 2 be continuous? Well, first check, does the limit exist? Well, we can see that the limit does exist here. See, if I go to the two-sided limit exists, it's going to be 1. But when I evaluate f of x at 2, what do I get out? I get out 2. 2 is not the same as 1. So notice the notation used to say here. We say the limit of f of x as x approaches 2 equals 1, but 1 does not equal f of 2. I'm going to show you some more notation on how you can prove or disprove something is or is not continuous. And in this last component, any value less than 0 or more than 4 is automatically not going to be continuous or discontinuous. It doesn't exist, so we can't evaluate it, because if I'm less than 0, I'm on this side. If I'm more than 4, I'm on this side. So let's look at our definition of what it says. We're going to skip this. We're going to go right to here. It says, if a function f is not continuous at a point c, we say that f is discontinuous at c, and that c is a point of discontinuity of f. Okay, and note that the c value doesn't have to necessarily be a value in the domain of f. Okay.